In this video, we'll discuss the so-called superposition principle. This principle will allow us to solve initial value problems for non-homogeneous differential equations. The theorem states the following. If y1 is a solution to the differential equation a y double prime plus by prime plus cy equals f1 of t, and y2 is a solution to ay double prime plus by prime plus cy equals f2 of t, then for any constants k1 and k2, the function k1 y1 plus k2 y2 is a solution to the differential equation ay double prime plus by prime plus cy equals k1 times f1 of t plus k2 times f2 of t. So let's first prove this and then see how we can use this. So what we're going to do is we're going to let y equal k1 y1 plus k2 y2. And now what we need to show is that this is a solution to the following differential equation. So we need to show that if we do a times y double prime and then plus b times y prime and then plus c times y that equals k1 times y1 plus, or sorry, k1 times f1 plus k2 times f2. So let's go ahead and write this out. So this, we're going to start with the left-hand side. So we have a times, and then the derivative of y is k1 y1 double prime plus k2 y2 double prime. And that's because k1 and k2 are constants, and so we can just pull that outside when we take the derivative. So then we have plus b times, and then y prime is given by k1 y1 prime plus k2 y2 prime and then finally we have c times y, and y is equal to k1 y1 plus k2 y2. So let's reorganize that a little bit. So I want to organize it so that I have all the y1s together and all the y2s together. So what I see here is that if I take the k1 and the y1 double prime, I can rewrite that as k1. Actually, let's write that in green. So I have k1, and I'm going to factor that out, and then k1 times a and then y double prime, y1 double prime. And then the other thing I have with k1 is b times y1 prime. So I also have plus b times y1 prime. And then finally, I have the c times k1 y1. So the k1 is factored out. So I have c times y1. And then the second part, I can factor out a k1 or a k2. So when I factor out a k2, I then get, very similar to the other one, a times y2 double prime, right? That's a k2 y2 prime, factor out the k2, and I'm left with a times y2 double prime. And then plus b times y2 prime. And then plus c times y1 or y2. Now, a times y1 double prime plus b times y1 prime plus c times y1, that is, since y1 is a solution to this differential equation, this right here is just f1. And then similarly, this differential equation, since y2 is a solution to this differential equation, it's equal to f2. And so this differential equation now is equal to k1 times f1 plus k2 times f2. And that is what we had to show. We had to show that ay double prime plus by prime plus cy equals k1 times f1 plus k2 times f2. Okay, let's see how we can start using this superposition principle. So we have to find a particular solution to the differential equation y double prime plus 3y prime plus 2y equals negative 9t plus 20e to the power 3t. And we're given that y1 of t equals 3 over 2 times t minus 9 over 4 is a solution to y double prime plus 3y prime plus 2y equals 3t. And y2 of t equals 1/2 e to the power 3t is a solution to y double prime plus 3y prime plus 2y equals 10 to the power, or 10 times e to the power 3t. Now, what you need to notice here is that the left-hand side is the same for all of these differential equations, right? So they're all y double prime plus 3y prime plus 2y. Now, this is a particular solution to the differential equation where the right-hand side is 3t. Now let's compare and find a function that's similar to that. And when we look here, we see negative 9t and we see 3t here. So what we can do is we can call this function f1 so that y1 is the solution to the differential equation where the right-hand side is f1. And then what we see is that negative 9t, that is negative 3 f1 of t. right? Negative 3 times 3t is negative 9t. On the other hand, we have 10 times 3 or times e to the power 3t, and we can call that f2 of t. And here on the right hand side, that's a function that very much looks like f2. In fact, this would be plus 2 times f2 of t. So now we want to combine these two functions, the y1 and the y2, to get the general solution. And so the general solution will look as follows. So y, or not the general solution, I should say, the particular solution looks as follows. Y of t equals this one right here, that coefficient. So it's negative 3 times y1 of t, and then plus 2 times y2 of t, right? Because y1 solves this differential equation and y2 solves this equation. And so by the superposition principle, the linear combination of these two will then solve this differential equation. So we'll write that out. So we then get negative 3 times y1, which is 3 over 2t minus 9 over 4, and then plus 2 times 10 e to the power 3t, that's y2. Sorry, y2 is I got that mixed up. So y2, look over here, y over 2 is 1/2 e to the power 3t. So I do 2 times 1/2 e to the power 3t. And then what I can do is I can simplify that answer a little bit, and I get negative 9 over 2t plus 27 over 4, and then plus e to the power 3t. And so this equation right here is a particular solution to the differential equation.